Hey everybody! So, as you probably all know, today we're going to be talking about quantum cryptography. And when I say cryptography, I mean specifically the field of breaking cryptography, because though we are white hat, we do also enjoy breaking things. So, just a little bit about me. My name is Gonella. I'm a second-year computer science student here, and I'm also I'm the old treasurer and the new CTF master for White Hat. I'm also, in addition to computer science, a mathematics minor and a huge enthusiast for math and physics. But more importantly is what I am not. I am not Albert Einstein. I am not a physicist. So we're going to do a little bit of hand waving in the quantum area. I'm going to explain to you what you need to know. But if you want to know more detail about it, I told my roommates this. This was actually originally a 3-hour talk that I pared down. So if you want more information, come talk to me. I know things. The other thing I'm not is a cryptographer, professionally. I enjoy cryptography. It's a really cool field. I highly recommend you look into it if it interests you. But I'm not a professional. So if you hear me say something wrong, because I'm also not the Pope. I'm not infallible. So if you hear me say something wrong, speak up. I probably am. I don't know. But anyways, onwards. So the world is very reliant on cryptography. We keep some of our most important things under lock and key in cryptography. And basically, we're going to define cryptography as the ability to take a piece of data and turn it into something that you cannot derive the original meaning of that data from. So for example, if I'm going to take a big text file with maybe my plans for how to take over the world, if I encrypt that, then no one can see it unless I want them to see it. But should we really trust crypto? Like, should we really trust this stuff? Well, first, before we talk about breaking it, we need to understand a little bit about the different types of cryptography. So there's two major categories, and the first is symmetric encryption. Now, this is the standard, more traditionally thought of metric of the same key or password will encrypt and decrypt the data. So an example I actually used earlier today is your phone. Your phone is symmetrically encrypted because you set the initial lock with your 4-digit PIN code, and then you open the phone again with that same 4-digit PIN code. So this idea of symmetric, the same key. On the other hand, we have asymmetric encryption. Now this is a newer form of encryption that relies heavily on the realm of number theory and group theory in order to create this interesting situation where you can take a piece of data, encrypt it with one key, and then decrypt that data with a completely different key. And the benefit for this is if I have these two keys, I can give the encryption key, or what we call the public key, I can give that out to everyone in the world. And from that, everyone will be able to encrypt things to me, but only I can decrypt things with the decryption key, which is called the private key. So this idea of public and private keys is incredibly important to asymmetric cryptography because it allows us to allow anyone to encrypt something to us, but only I can decrypt it. So if we have this amazing system of asymmetric, why don't we use just it? But we can use both. The reason we use both is because they have trade-offs. On one hand, you have symmetric encryption, which is much faster. It's much less resource intensive to do than asymmetric, but it suffers from something called the codebook problem. And the way I describe the codebook problem is, let's say that I want to encrypt a message to send to Nathan. Well, in order to send that message, first I need to share the symmetric key with him so that we can both read and encrypt it. How do I get him the key? Well, I guess I'll have to encrypt that key with another key. But then how do I get that key to him? So on and so forth. And the reason it's actually called the codebook problem is because back in the old days, the way they would do it is you just have, oh, no, what? Back in the old days. Now, as I was saying, symmetric encryption suffers from this thing called the codebook problem, which is the idea of trying to share the key to encrypt it and needing to have some way to transport that key securely and it being this big recursive problem. So on the other hand, you have things like asymmetric, where you can share that initial key with everyone, and you don't have the codebook problem because the key that you share is different than the key that you keep. And so the way that we use this is we actually do both. So this idea of Diffie-Hellman is the use of asymmetric encryption to share a symmetric key. So you only need to do one resource-expensive asymmetric encryption, and then you have mostly safely shared key that you can now use for symmetric encryption. And so SSL implements this, which is the protocol if you've ever used HTTP versus HTTPS. HTTPS is using SSL. So before we go on, does anyone have any questions about the ideas behind symmetric and asymmetric cryptography or what those really are? Cool. Then the next thing I want to talk about is RSA. So RSA is one way to do asymmetric cryptography. And it basically revolves around this idea of there being a problem that's really hard to do, really easy to do, and really hard to undo. In this case, factoring. So if I take two really, really large prime numbers and multiply them together, doing that multiplication is really easy. It's one instruction, maybe two. But undoing that, finding the two primes from that one big number, is an incredibly difficult problem. It's computationally expensive. It's what you call it's a super polynomial time. So it takes longer, it takes a very large amount of time in order to do this prime factorization. And so we say that this problem has a good ratio. It's the ratio of difficulty to do versus difficulty to undo is very high. Now, finally, Ryan?
But are they actually prime?
So yes, they are actually. So the numbers used for RSA are actually prime. They have to be, or else the crypto system would fall apart.
They're not just very likely to be prime?
No. If they were only So the way we actually get those primes is we have a giant table of primes that RSA will just pick two from at random. So they're pre-computed primes, but you have to use two prime numbers or else the number theory backing RSA will keel over and you won't be able to decrypt it.
Yeah, because then the security guarantee is no longer based on the fact that you need that n-squared algorithm at the core to even detect a prime.
Yep.
Okay. Huh.
I don't believe it pre-computes them. I think it has a generator. I think it uses some mathematical generation to generate them. But
I've always, why I asked is because I've heard that the way that they come up with the primes is doesn't guarantee a prime number, but
They guess pseudo primes and then check them.
Yeah.
So
It also verifies.
the generator is fast enough that they can almost always get a prime, and they check it, and then if it's not a prime, they just generate another one. And it's efficient enough they don't have to do that more than once or twice.
Huh.
So that's how they do it on larger systems, but on things like embedded systems, there's a stuck-in table of primes that it chooses from. But yes, on larger systems where you have those resources, you can also generate pseudo-primes and check them. But again, checking for primes is about as hard as cracking them, so because you have to find out if you can't crack them. So, now that we have a little bit of understanding of the backing of RSA, let's go on to the onto the quantum. So, quantum mechanics is a relatively new field in quantum physics. It really started development it started taking off about in the 60s or 70s with some not the 60s or 70s, the 20s or 30s with some major discoveries by Albert Einstein, who actually famously did not believe in his own work. There are a couple funny quotes by him on that. But in the quantum world, there are a few things that are very different from the classical world or the larger scale world. And the one I want to talk to you about today is the ideas of superposition and duality. So again, these are really big concepts in quantum physics, and if any of you are quantum physicists, I'm sorry, I'm going to gloss over some parts. If you'd like to clarify, I'd love to talk with you about it afterwards. So the first one we're going to talk about is this idea of superposition. So in the traditional sense, I could be standing right here, or I could be standing over here. I could be picking up this clicker, or I could not be picking up this clicker. But I can't be both at the same time. I cannot be simultaneously doing an action and not doing an action. But in the quantum world, you can. You can have a photon that is in the state of both. For example, if we're looking at photons like bits, 1 and 0, a bit can't be both 0 and 1 at the same time. But a photon can. A photon can exist in both mutually exclusive states simultaneously. It's really strange, it's very cool, but we can leverage this fact that they exist in two states at once to make computing things faster, because we can compute on both of those states at the same time, which tears down our computing. Now, the other property that's important to this is this idea of duality, and that's the idea of particles and waves. So in the macroscopic world, we could have a bunch of dots, for example, and we would look at those as discrete little dots. But as we make those dots smaller, and as we make the intervals between them smaller, if we get to the quantum scale, we can treat those dots as just one wave. So in quantum mechanics, a string of photons is also a wave. It's another strange property, and it's this idea of duality, that you can look at these at a wave as a string of photons and a string of photons as a wave based on which properties help you out more. And we're going to be leveraging that property today in breaking some cryptographic systems. So I mentioned this already, but why does this help? Well, because of this superposition of states, we can do simultaneous calculations very easily. So if any of you have done the parallel class here, certain problems can be done parallel. For example, last quarter we had a talk about cracking hashes by Jonathan Nicholson. So in that talk, we talked about how we were using the GPU to calculate multiple numbers at the same time that were independent of each other. Well, this same idea can be taken to quantum. Because we're calculating on the one state of the photons and the 0 state photons at the same time, we get simultaneous computation. Before I go on, does anyone have any questions about that? Yeah? Okay. Cool. Yeah?
Is this kind of like non-deterministic finite automaton that they talk about in like theory of computing and stuff, where you're kind of in two different states simultaneously, like conveniently just...
That sounds right. I have not taken theory of computing, so I do not know what a non-deterministic finite state. I do know that quantum computers do actually come out to be non-deterministic, so we're going to get to this a little later in slides, but the solutions you're going to get to this are with a high probability of being correct, but you can't actually guarantee 100% a correct solution because everything in quantum is probabilistic. But so I don't know if it's counts as a non-deterministic finite state automata, but that sounds correct. So the other thing I want to take you away from this is you can't solve every parallelizable problem with quantum states. They have to be something called a collapsible state problem. And what that basically means is that you have to be able to somehow leverage that duality that we mentioned of, because you're looking at a string of particles as a wave, or you're looking at a wave as a string of particles, because you can collapse that state into the other, it makes it faster. So there's only certain problems that are actually collapsible state. And we're going to see that we can leverage one of those problems to do factorization, because RSA is broken. RSA is the most common method for asymmetric encryption. And actually, I don't know the additional statistics, but it's something in above 90% of the asymmetric cryptography is done with RSA. And using this thing called Shor's algorithm, which is a quantum algorithm, something that leverages a quantum computer, we're going to break RSA. So this is going to come in two parts. The first is called a problem reduction, where we turn one kind of problem into another. And the second is a quantum Fourier transformation, where we take that problem that we've created and solve it using quantum computing. So first, let's talk a little bit about the problem reduction. As it turns out, factoring two numbers is not a state collapsible problem. You cannot just straight up factor two numbers using a quantum computer. It'll be just as slow as a traditional computer. Which is unfortunate because, you know, we really want to break that crypto. We really want to get into it. So we say, all right, if we can't solve factoring, is there a problem that we can solve that we can then use that problem to solve factoring? And the answer to that is yes. There's another problem in number theory called order finding. And I'll talk a little bit about what order finding is on the next slide. But there is this problem, order finding, where we can say, all right, if we can solve the order finding problem, then we can definitely solve the factorization problem by some transposition. So there is some function that we put the solution to the order finding problem into, and that will give us the answer to our factorization problem. And this is a classical reduction, which means we don't even need our quantum computer for this part. We can do this now. We can turn factorization into order finding, which is actually how the current most powerful non-quantum algorithm for factoring works. It converts this order finding problem and then solves it in a non-quantum way. But we're going to take a step forward and say, all right, we have the order finding, so how do we solve it in a quantum way? So what is order finding? Well, let's consider the 2 to the r series. We have 1, 2, 4, 8, 16, 32, 64. Some of you who are in 357 are currently having Vietnam flashbacks because I've forced you to memorize all of these. But now what happens if we do that series modulus 15? And what modulus basically means is we take a number, we take 2 to the r, divide it by 15, and keep the remainder. When we start to see this interesting pattern, 1 mod 15 is 1, 2 mod 15 is 2, 4, 8, and then it repeats. So we have 1, 2, 4, 8, 1, 2, 4, 8, and it will actually repeat in this period. And the order of this series is 4, because at 2 to the 4th, that's where the 1 repeats. That is where we have this repeated 1. And so that's the order finding problem. It's given a certain series of n to the x, or number to the r mod some other number, can we find the order of that sequence? And now what we're going to do is we're going to superimpose stuff. So I mentioned a little bit earlier the idea of quantum bits, or as we call them in quantum computing, qubits, existing in multiple states at once. And this being called superposition. So if we're able to get 2 to the n quantum bits, and n, this is just basically the number of bits that it would take to store a specific number. So for example, if our n were 120, then 2 to the n would be 6. No, 7. I can do math. It would be 7 because 7 bits are required to hold the number 120. So we're going to superimpose every solution to x to the n. We're going to superimpose every solution to number to the r mod number, sort of like this, onto those bits. So we're going to have each pair superimposed onto the quantum bits. And this is actually where, like, we actually can't do this right now. So Shor's algorithm can't be done in real life. We have not found the ability to hold enough bits past, I think, 5 right now. We haven't been able to hold more than 5 bits in this superposition for long enough to apply Shor's algorithm. So this is all theoretical. But if we were able to do that, if we were able to hold it, then we'd have all of these bits in superposition with each other. And that's kind of an abstract concept. So does anyone have any questions about that, about this idea of superimposing a bunch of different states on top of each other? Making sense? Maybe? Yeah.
I'm confused where the wave is coming, because you said it could be like a 1 or a 0.
I'm getting
both at the same time.
Yeah, I'm getting to where the
It's analog.
I'm getting to where the wave comes in, I promise. Right now we're just thinking about photons, just the individual particles put in line right next to each other, all existing in a number in every different solution to the number to the power mod other number problem of every one of those at the same time. Cool? So the cool thing about this is then we can leverage duality. Because when we impose those things together, we then say, all right, so we have this string of quantum bits. What happens if we look at it like a wave? Well, coolly enough, it creates this wave. And the idea is this, this is a sine, basically this idea of a sine wave where every point is, you have a point that is 1 x to the 1, 2 x to the 2, and you create this period. So then if you can find the period of this wave, then that's the answer to your order finding problem. Because it's how long it takes for the wave to repeat at this median. Well, fortunately, we have this cool little tool called the quantum Fourier transform. And what a Fourier transform basically does is it takes any wave that we give it and finds the frequency of it. And the frequency is just 1 over the period. So what we do is we take this string of quantum bits that we've held in a superimposed state, apply the quantum Fourier transform, and what I mean by apply is in theoretic terms, we apply a mathematical function to it. In actuality, we apply this long string of hardware to it that honestly was scary. If you want to talk to me or with Nate about it a little more afterwards, yeah, I'm involving you in this. But basically, we do it, and we get a set of possible positive and negative frequencies that this thing could be. Then we sum all those frequencies, and because of the way that quantum Fourier transform works, everything interferes except the true frequency. So all the frequencies add up, so you just have the true frequency left. Then you just do 1 over that, and you have solved the order finding problem. And in turn, you can transform that back into the factorization problem. So in this last step, again, does anyone have any questions? I had to do a little bit of hand waving with this because the actual implementation doesn't exist yet because we can't hold this many bits in superposition, but does anyone sort of get this idea of we transform the problem into something that can be done in a wave-like fashion, then we superimpose all of those states onto the quantum bits, and then finally we apply the Fourier transform that looks at the wave instead of the quantum bits and finds the period of it. What's up?
Is the QFT the dominating term in the complexity of this algorithm? Or the multiple algorithms that are being chained together?
Actually, it's not. The current dominating term is the idea of calculating each number to the power mod something, calculating each of those, and putting them on top of each other. That process takes a while because you still have to calculate all of them. So the dominating term is this second part, this superposition. The QFT is actually a pretty fast algorithm because it's basically just doing analysis on the wave. It doesn't have to generate the waveform itself. Did you have a question?
I'm curious how we get from the taking the mod to the graph with the wave.
Okay, yeah. So we have the taking the mod, which we see here is it's periodic. It oscillates sort of like a wave. Right? Because we have 1, 2, you could almost imagine we have 1, 2, 4, 8, 1, 2, 4, 8. You can also almost imagine it like a sawtooth wave going up and down.
The wave goes from -8 to +8?
Well, no, in this case it's sawtooth. So it's not an exact correlation, but in this case it looks like a sawtooth. But when we superimpose all of these states, so we say, all right, now take our string of quantum bits. Now set them equal to 1 and 2, or set them to 1 and 2 and 4 and 8 and 1 and 2 and 4 and 8. Obviously, this would be with a much bigger number where the period is much larger, but we're using a small example. If we set it to all those states at the same time, then it creates this wave. And this wave has a period equal to the solution of the order finding problem. Nate?
So one thing that Fourier transforms need is a certain amount of ordering in the samples. So when you set it to a superposition, how do you get it in order so that it can actually find the period? Because if you just have them in superposition, it's just a big mass of stuff.
So you're not actually looking at the superposition, you're looking at the wave that's created from the superposition.
So as you impose each state onto the bits, you then sample that and perform a Fourier transform on that, or?
Basically, yes. A quantum Fourier transform is more, it's not so much like a discrete Fourier transform. A discrete Fourier transform is where you do sampling on a wave, but you actually have this pure wave at your disposal, and the technicalities of how you have that is sort of due to the quantum nature and the quantum nature of it. But you have this this sinusoidal wave is available to the Fourier transform, so it's much easier to find the period.
Okay, so it is more of a continuous Fourier transform.
Yes, it is a continuous Fourier transform.
Okay.
Yeah.
Oh wait. Oh, so as you apply a state onto the qubits, so as you apply those states, it creates this wave, and then you apply the QFT on that.
Yeah, wait 1 second, I accidentally unplugged this. My bad.
So yes, as you apply each state onto it, it gets onto the superposition of bits. It looks more and more like the wave itself until when you finally apply to all of them, you then look at it as a wave, and it becomes the wave that we're looking at.
All right, that makes sense.
Cool. These are all really good questions. Like this topic, like this idea of switching from perspective of a bunch of just bits that seem to be random to like this nice discrete wave, or not discrete, but this nice clean wave is really trippy. It's actually kind of cool. So, does this really matter? Yes, it does. These are the big O notation. These are the big O complexities for Shor's algorithm versus the traditional algorithm. And if you haven't done big O notation yet, basically it's this idea of what is the proportional worst case for this algorithm. And even if you don't know the technicalities, if you just look, this is going to be, if you put in n here, this is going to be a much larger number than this is. Like, if you were to put, I think the statistic was if we had quantum computers today, we should trust DES more than RSA to keep our data safe. And so basically I mentioned DES, why DES? Won't that be equally broken? Well, no, because quantum computing, again, only works on specific problems. It only works on the problems that help asymmetric cryptography. Most of our symmetric schemes would actually still be safe if we had quantum computers, because they solve a different class of problems. So, the end is nigh, maybe. I like to think of quantum computing sort of like Sour Patch Kids, if you've ever seen the commercial. First, they're sour, and they break all of your asymmetric encryption in the world. But then they're sweet, because they give you quantum key distribution, which is another method of asymmetric encryption that is not vulnerable to Shor's algorithm. So basically, all quantum computing does is destroy everything you know, and then make a new method. So the only problem with this would have to be getting people to implement it and getting people to upgrade, which has never been a problem in computer science.
Does it also break like Diffie-Hellman exchanges, or just prime exponentiation?
It also breaks
exponentiation too.
It also breaks Diffie-Hellman.
That's not good.
Yeah, nope. This is basically, even if any of you were here last year, I gave a talk on elliptic curve cryptography. You can turn the elliptic curve cryptography adding problem into a factoring problem, and then turn the factoring problem into the ordering problem, solve the ordering problem with Shor's, and then go back through the two, break elliptic curve. And so yes, even my beloved elliptic curve will not be safe. But we have a new one, quantum key distribution. It's really cool. That was where the other 2 hours of talk were gonna be, but I figured y'all didn't want to hear that. So basically, we have this really cool thing where, though Shor's algorithm breaks modern asymmetric encryption, it replaces it, and there's plenty of other really cool quantum algorithms. So there's hidden subgroup problem, which is basically, I don't want to explain that. Hidden subgroup problem is basically being able to find certain properties of commutative groups. So for example, finding certain properties of what groups are similar to the integers or the real numbers, but with other things. Hidden subgroup is part of the way that you break ECC with quantum cryptography. You also have quantum phase estimation, which is the second half of Shor's algorithm, where you basically can find a way to find the phase of a wave really easily with that quantum Fourier transform. It's much faster than something like a discrete or continuous Fourier transform. And the last is advanced modeling engines. So it takes physics to know physics is sort of my take on that. If you really want to model the specifics of quantum mechanics and quantum dynamics, you kind of need a quantum computer to do that level of calculation. So what do I want you to take away from this? All of this is really pretty theoretical. We can't hold more than 5 bits in superposition right now, so we're very far away from the end of RSA as we know it, but there is research in the field. We are slowly being able to hold more states over longer. We're actually currently using the common link between quantum physics and the Java constructor. That is spooky action at a distance, or otherwise known as entanglement. So at the beginning of the talk, I asked, should we trust crypto? And the answer is yes. You should trust your crypto, encrypt your things. They're safer that way. They won't steal your dank memes. And I want to finish with, the world is filled with really strange problems, especially in CS, so go find some fun ones to solve, because I guarantee you'll enjoy it. Thanks for bearing with me on a very technical, very mathy talk. Here's a comic for you. Any questions? We kind of did.
So obviously it's going to be a while before, so like the NSA will get these quantum computers and be able to break everything. And then it will be a while
Or already
before
have them.
everybody else gets them. So what should we do before we can use that quantum method of encrypting in the interim?
Well, there's a number of things you could do. You could go to an alternate solution for the codebook problem and just use symmetric keys if you're really paranoid. Although so this is going on the internet, so I'm going to be careful about what I say, but no, I'm kidding. Certain 3-letter agencies may or may not already know how to crack RSA / have prime numbers that people use pre-computed to crack. So you might be screwed already, but basically, it all comes down to threat modeling. So if you're really worried about a nation state or something like a 3-letter agency breaking into your stuff, like either you're screwed or you really need to go for drastic measures. Like there's just, with something like the NSA or other 3-letter organizations, they have so much resources that without really drastic action, you just kind of got to accept that they're going to break your shit. Any other questions? Max?
So is big quantum the new big cyber?
Actually, this is the new field that I'll be studying. The big quantum cyber data. Yeah. What?
Do you have any wrenches for sale?
No. You'll have to wrench mine from my hands. All right, I tried. All right, cool.
Thanks, Luke.
Cool. See you around.